morning, everybody. It sounds like you woke up a little bit. Just a little bit. The coffee has started working its way through the system.
Yeah.
I don't drink coffee, so I wouldn't know, but a cold shower does wonders too. Nope.
No tea?
No, I drink water.
H2O.
I'm boring that way. You might be able to get me every once in a while to drink a soda if it's summertime and I'm sitting on the porch. Maybe, but hot chocolate. I'll do a hot chocolate.
Hot chocolate, yeah.
We let's see. I've been torturing you with all kinds of math, haven't I? So I'd like to tell you that it's going to get better today, but it's not. It's going to get a lot worse. It's going to be terrible. But I do want to give you a little bit of hope. Okay? Starting Wednesday, when I get to chapter 7, hoping you get chapter 6 done today. When I get to chapter 7, we are going to start looking at everything we've done so far in the class from a different point of view. And importantly, that point of view is going to remove vectors from what we're doing. It's called energy and conservation of energy, so I think you'll be much happier campers when we finally get there. But we do have to pay the price, getting through Newton's laws. And today, it's time to add friction. Now, one of the things that I get a lot as a physics professor is, well, Mr. Baylor, you never do anything real. That's a good point, right? Physicists are famous for like, wow, just ignore everything that's hard, right? Make the engineers do the hard stuff. We have our moments. We get into the hard stuff, and there are lots of problems we solve where we don't ignore everything. And again, why is it that we tend to sort of throw away air friction and not worry about complex interactions? Why are we doing that with you? It's easier to get used to the problem solving and the concepts. And quite frankly, it's really good approximations for what actually happens. Most of the time when you say are throwing a ball through the air, you don't really have to worry about the air resistance. Does it affect the time of flight of the ball? Sure. But only by like maybe 0.05 of a second, right? So unless you really need to be that precise, it's all right. So we can play fast and loose with that. But what we're doing now is we're going to bring friction back in. Where before we ignored it, we're going to bring it back in today. And so we need to talk about the two different kinds of friction that physicists have categorized. What I want you to do is do a little experiment right now. I just want you to put your hands together, okay, like this, and rub them, right, as if you want. So what do you feel? Heat. You feel heat, okay. So what's happening there is your hands are warming up because of the friction between your hands. Now, that's a very different kind of friction from the next thing I want you to do. I want you to put your hands together and try to do that rubbing motion, but I want you to push hard enough where your hands can't slide, right? So are you getting any heat generation there?
No.
No, okay? Here, there's no relative motion between the surfaces, right? With first hand, when you're warming your hands up, here the two surfaces are sliding against each other, but here they're not. And friction is involved in both cases. For sliding, we call that kinetic friction. What does the word kinetic imply? Movement or motion. Static friction, the friction that exists between things where their surfaces aren't moving relative to each other, okay, turns out to be the stronger of the two. So we have kinetic and we have static. Have you ever had to help somebody move a big piece of furniture? Yeah. And maybe it's sitting on the carpet or a rug or not a really smooth floor, right? When you come up to that piece of furniture, how hard is it to get that piece of furniture just moving?
Hard, but it's easier.
Once it's moving, it's easier, isn't it? Okay? But that initial kind of, right, to get it going seems much harder than once it is going. There's two things happening there. First of all, once you've got it going, Newton's first law applies and objects want to maintain their state of motion. So the inertia of the heavy object is helping you keep it going, right? But the other thing that's going on there is the static friction between the floor and the object is much stronger than the kinetic friction that exists once the object begins sliding. Kinetic friction is always weaker than static friction. Now, static friction gets us in trouble in a lot of different ways. So, what kind of friction exists between the box and the desk? It's kinetic. And how do you know it's kinetic? Okay. Now, Mr. Balo yelled at you for saying things like, well, it's moving. Right? Now, but in this case, can we say that? Yes, but again, we have to be kind of careful. What do we mean by it's moving? Okay. What kind of friction exists between the box and the tape dispenser? That's static. But it's moving. What do we have to key in on? The relative motion. The surface of contact between the tape dispenser and the box. Okay? That's not moving, so that's static friction. However, there is kinetic friction between the box and the table because the two surfaces are moving relative to each other. The friction that exists between your car's tires and the road. Kinetic or static friction?
Static. Partially static right now.
It doesn't matter if it's parked or moving. But let's just say it's moving. Static friction between your tires and the road, because if it wasn't static, it would be kinetic, and that would mean your car would be in a skid. That's not good. What is it that an anti-lock braking system is supposed to prevent?
Your brakes from locking.
It is there to make sure that the friction between the road and your tires is always static. Anti-lock means the wheels will continue to spin even when you're braking. In the olden days, you hit the brakes, you could actually stop the wheels from turning, but the car was still moving, right? There, the tire is rubbing across the surface of the road, and the braking distance was much longer. As long as you can maintain the tire turning, make sure the patch of rubber and the road are not moving relative to each other. Your car's going forward, but your tire at the bottom is going backward, right? And if you can keep the friction static, you can reduce the braking distance. Walking across campus. Ooh. Yeah. You take that step, right? And you walk forward. What kind of friction exists between your shoe and the ground?
Static.
You sure?
Yes.
Why?
Because
Because if it was kinetic, you'd be ice skating. Right? You would be I can't do the moonwalk, right? But you would be slipping all over the place, wouldn't you? Right? If it were kinetic friction. But this is static friction. Now, when a person, like in baseball, goes in to slide into second base, yeah, I know that much. You don't slide into first base. Kinetic or static friction? Kinetic? The baseball player is sliding across the ground? Yeah, that's kinetic. Okay? What direction is the force of friction on the baseball player? Opposite the direction of motion, right? As they slide into second base, friction is acting the opposite way to slow them down. All right, what direction is the static friction between your shoe and the ground? Well, the up would be the normal force. That's not friction, right? But what direction does the friction point when you take that step? Okay, So I've got a forwards direction, backwards direction. Everybody votes. There's no third answer on this one. It's either forwards or backwards. Okay, right? Okay. So what I want you to do right now is point in the direction that friction is acting. Everybody point. Okay. All of you that are pointing forwards are correct. Why did you want to point backwards? Because backwards is the direction that I apply to the ground. I plant my foot, I push on the ground backwards. I know there's downwards, we'll talk about that in a minute. Backwards, right? And the friction, what's the force that's moving me forwards? Friction. If there were no friction, what would happen? Right? I wouldn't get anywhere. So the static friction here is causing me to move forward. Kinetic friction always opposes the direction of motion. Always. Kinetic friction, you can take that one home. There's never going to be a case where the kinetic friction acts with the motion. Always acts against the direction of motion. Static friction, on the other hand, static friction can act either with the motion or against the motion. It really kind of depends on the situation. So be careful with static friction. It can really come and bite you. All right. Well, what are we going to do about this, and how are we going to kind of mathematically formalize those ideas and concepts? Well, the first and chief thing that we're going to do is that we are going to remember how much fun friction can be. So little curly f is a symbol we tend to use for friction. Sometimes you'll see capital F, sub small curly f, right? But generally we just go straight for the small curly f. That indicates friction is happening somewhere. The N in there, what's N? Normal force. So here, the relationship between friction and normal force is direct. The more normal force there is, the stronger friction can be between the two surfaces. Cars are designed to take advantage of this. The harder a car can push down on the ground, the better the traction of the tires will be. In fact, in race cars, Formula One cars, they design the shape of the car to be basically the opposite of a wing, an upside-down wing. Instead of a wing which would try to lift something up, a race car's shape is a wing that pushes it into the ground. The more that they can push that car into the ground, the better the traction will be, the faster they can corner. As a matter of fact, for some of those vehicles in certain classifications of race cars, they push down so hard with what's called downforce, because of the wings and everything they've got on the car. They push down so hard that the force pushing down is twice the weight of the car. Now, the cars aren't heavy. They're made out of all kinds of space-age materials and carbon fibers and things like that. But what this means is once those cars get above 80, 90 kilometers per hour and that downforce begins to really ramp up with speed, and then they get up to 150 miles an hour, they could get on the track, get upside down, and be held onto the surface of the track. Because the downforce, right, pulling them into the track exceeds their weight by a factor of 2. Now, I'd watch that. Just don't slow down. No braking. All right. So this mu in here, that's the Greek letter mu. Don't have any pens. It's a U, right? But it's got a trunk or something on the front. I'm not sure what that is, right? Okay. But one of the many languages you are going to learn in this class, one of them is going to be ancient Greek. Use a lot of Greek symbols. We start running out of letters of the alphabet. Several years ago, I tried a movement to go to Chinese characters, but nobody would. All right. So what is that thing? It's called the coefficient of friction. What are its units? What are the units of mu?
None.
What are the units of friction? Force of friction? Newtons. What are the units of a normal force? Newtons. When you take a Newton, divide by Newton, what do you get? Nothing. The coefficient of friction is a unitless value, and its job is to tell us how strong the friction is. It is entirely dependent on the materials and the quality of the surface of contact between those materials. So like ice, like an ice rink against a steel ice skating blade. That has a really low coefficient of friction. Rubber on a road has a higher coefficient of friction. Generally, it's a number between 0 and 1. 0 for no friction at all, 1 for really high friction. So like your car tires against the road, that's like a 0.4, 0.3 or 0.4. Same thing for your shoes on the ground, slightly less, like a 0.25. Sandpaper, okay, is way up there, sometimes above 1, depending on the type of sandpaper and what you're doing. But generally, it's a decimal value of some sort, some number between 0 and 1, usually between 0 and 0.5. All right. Sometimes you will see in various books or online or something like that, your book does this, you'll see like an F sub S or an F sub K, or maybe not even that. They'll just write their fun equation with a mu sub S or a mu sub K. What are they trying to tell you there? Either static or kinetic. And again, the coefficients change depending on whether you have static or kinetic friction. What do I mean by that? If we were to graph, say, coefficient versus time or something, or it doesn't really matter what the x-axis is, what we see is as long as an object maintains static friction, okay, static friction can vary. It is whatever it needs to be to make sure that the acceleration of the object is 0. But as soon as it begins to slide, right, then you have this kinetic value. And the kinetic value stays more or less constant. I made it a little bit wiggly in my picture because, kinetic friction can kind of like jerk a little bit in the motion. But we're going to assume that kinetic friction is the same regardless of how fast the object is moving. But static friction can take on any value, okay? Up into the point where you overcome static friction, and then it drops down into that kinetic regime. So you won't see me really write sub S or sub K. We'll know in the setup of the problem whether or not something is sliding or not. Okay, and then I just write fun, and away we go. Okay, so let's do some examples where we add friction. That's all I'm going to do. I'm just going to add one force to the examples we did last week. That's it. How bad could it be?
That should be your catchphrase. Get a shirt about that.
Yeah, along with, that's, how hard could it be? So, let's see, in this class it was a tauntaun, wasn't it? Sliding tauntauns down the, did anybody go out and watch Empire Strikes Back? No. Shame on you. All right, so let's go back to our hill, okay? Have you noticed how the examples in these last two chapters I haven't written down any word problems for? Before in kinematics, it would give you situations with word problems. Here I'm not doing that because even though you're going to have a lot of word problems in physics, generally life does not give you word problems. Instead, what it gives you is life. The universe just happens. And then we have to put it into a word problem so that we can then go and solve, right? This is even worse than you thought. Not only is the class full of word problems, but you've got to figure out what the word problems are. All right, so we're going to do the tauntaun from Empire Strikes Back. And this time, though, we are going to include friction. So this tauntaun is sliding down the slope. I'm telling you that right out of the gate. Before it was sliding down the slope, but we said it was frictionless. This time, we have to take into account friction. We are only adding the one force, but the rest of our problem-solving method stays the same. So what I would like you to do right now in your notes, okay, is draw the free body diagram for the tauntaun. Give you a chance to do it on your own. So we're looking at the free body diagram for the object sliding down the hill. Go ahead and draw that. As you draw this, you should be thinking about the questions I told you you should be asking. Alright, I'm going to do something mean right now. I didn't warn you ahead of time. What I want you to do right now is turn to the person next to you and share what you drew. Okay? And then you critique each other's diagrams. See if you agree on what you drew or not. Go. All right, is this what you got?
Yes.
Yes.
No? Yes? No?
I just added acceleration.
Where did you run into trouble?
Nowhere.
Monday morning.
Monday morning. Stroke of 6.
Nobody wants to admit where they ran into trouble? I can safely assume now everybody's an expert, so I can just give you the test now.
Yeah. Yes. Let's go.
To see if there's static friction.
Right, so I taught you about static and kinetic friction, right? So maybe there was some hesitancy there, and like, wait a second, but what did I say about the tauntaun in this problem? It is sliding, and as soon as we know that it's in motion and sliding down that hill, what kind of friction do we know it is? Gotta be kinetic. Okay? That's good. So how did I know to draw the force up the hill?
Opposite direction.
Kinetic friction always opposes the direction of motion. So when kinetic friction is involved, then we have to know what the motion is. There's really no way around that. However, this free body diagram is incorrect. You want to tell me what's wrong? Connor?
You're missing the axis and acceleration.
There you go. Okay? I don't have an axis defined. Okay? As far as I'm concerned, no definition of positive or negative means I don't really know what I'm doing. So it's one thing to get the forces down. It's another thing to make sure you can communicate and stay consistent with choices that are coming up in the future. So, what's Mr. Balow's rule of thumb for this? Put it in the direction of the acceleration. Now, we have to kind of... Is the situation one where the tauntaun starts at rest and is speeding up as it goes down the hill? Or is it the situation where the tauntaun was sliding but is slowing down as it gets to the bottom of the hill? Those are two different things that are happening, right? and we're just going to pick one for the purposes of showing this example. We're going to say that the tauntaun is speeding up. Started at rest and is going to pick up speed as it goes down the hill. So if it's picking up speed as it goes down the hill, which direction is the acceleration?
Downhill.
It's down the hill. So I'm going to go ahead and say, well, I know that my acceleration's that way, so what direction am I going to make positive x? I'm going to make positive x be down the hill. And which direction am I then forced to make positive y in? I've got one of two choices. It's got to be perpendicular to x. So I could make positive y down or into the hill, right? But I'm guessing that's making a lot of you uncomfortable.
Would that also include negatives?
Right, so as soon as you pick a positive direction, you picked your negative direction automatically.
Okay.
All right. Now that I got the coordinate system there, what do I do next? Are you having those moments during your homework where you're like, I drew the free body diagram, right? You should be celebrating at that point. I did it. And then you sit there going, what do I do next? Okay, you can jump right into the strategize portion, right? Because when it comes to Newton's second law, we know that we're going to have to break it up into x and y pieces of the motion. Okay, so yeah, let's go there. It's fine. Okay, so one object. So I think maybe I'll just do an x direction and y direction equations. That's going to be the mass times the acceleration in the x direction equals, and then I'll set it up because I know I'm going to be doing this later, right? And again, Mr. Balow writes Newton's second law with the MA first because I tend to forget it if I don't. Right? I try to focus too hard on these forces and forget what I'm doing overall. Okay, so now that I've gotten here, how am I going to write down the forces in the x direction?
It's just acceleration.
There is mgx in friction.
Somebody mentioning angles and thetas. What do we realize that we missed when we did our free body diagram? Breaking up. Making sure all of the forces are totally in x or totally in y. So two of these three forces are playing nice. And by that I mean they are already lying along an axis. Which two forces are already lying along an axis? Friction and normal force. So we don't have to go find components of those. That means mg we have to find components for. And like we did last time, we're going to drop a component. Technically, we could draw it down there, right? But I don't. I tend to draw it attached to my object. And if the angle theta is given, then what do I know about the angle that's sitting at the top of that vector triangle? It's the same. And again, you could come over here and draw a picture of just the vector all by itself. You could draw yourself maybe a little mini coordinate system and then draw the triangle so you can see what's going on. Okay? You'd have to say, well, I know theta's up there. I know this is a 90-degree angle because all the components are perpendicular to each other. And then now I can see really kind of straight away which one is which. That vertical component of the gravitational force, am I going to use sine or cosine? Why? Just touching the angle. And what about the one that points along the hill? Mg sine. Because it's not touching, right? All right, now that I've got them broken up, now I can go ahead and start writing down my forces, right? So do that right now in your notes. Write the x and y forces on the other side of those equal signs. Those are all the pieces. But what directions do they point? mg sine theta, positive or negative? Why? Pointing in the positive direction. We defined positive as down the slope. So it has to be a positive force. It's pointing down the slope. What about the friction? Negative. Why? Because it's pointing up the slope. Be careful. A lot of people want to say, well, it's friction. It's always negative. Yeah. Kinetic friction is always negative. And you're safe here because we're talking about kinetic friction. But I want you getting into the habit of just thinking a minus sign always goes on friction. Because sometimes there's static friction that makes things go. And there will be positive signs then. So make sure that you're arguing for direction based on what you chose directions to be. We chose positive to be down the slope. Friction points up the slope in the negative direction.
So when the ball's rolling downhill, does the static friction point forward?
We will handle rolling motion in chapter 12, I think, or something like that. Because that's a case where, because it can't roll without friction, right?
Yeah.
You have to have friction in order for something to roll down a hill. But it turns out that that static friction that exists there is only causing it to roll, it's not causing it to move. What's the force that causes it to roll down the hill? Gravity. Gravity moves it. Static friction allows it to rotate. And so we've got to get really into the weeds about rotational motion, tangential forces. Smiling. Sometimes I just wonder if that's too creepy. All right. What about the normal force? And mg cosine theta? All right. Like last time, we are after the acceleration of the tauntaun. Want to know what it is. And then after that, we could go off and do some kinematics to figure out other things. But we just want to know the acceleration of the tauntaun. What's the acceleration in the y direction? Because we made it that way, right? We guaranteed it's only going to be in the x direction. Hopefully you see here, by tilting the coordinate system, that we're really saving us a lot of vector nightmares. Right? Again, because it was tilted, even though we added another force, we still only have one of these forces that we need to find components for. If we had insisted on a perfectly horizontal, perfectly vertical coordinate system, then mg would be fine, and we'd have to find components for f, for n, and for a. Again, you can do, but why? It's too much work. All right. So we're going after the acceleration up there. Can I just go through and cancel these m's? No. Because it doesn't exist in the f term, does it? All right. What have I got here? I got MA equals MG. I'm just rewriting it. Sine theta minus F. And I've got to solve that for A. I know my M and I know my theta. But I don't know what F is.
Well, you can find MGY, and that'll be your normal force.
We have to remember how fun friction can be. You're already tired of that dad joke, aren't you? Don't forget fun! Because what does fun do?
Makes us miserable.
You win. It connects friction to normal force. Do you remember how last chapter I kept doing the y direction and then I kept saying, oh, this is useless, it's not helping us at all? Do we need the y direction now? Yes. Because if I insert this, I'm doing math now, by the way. The physics is on hold. The mathematical puzzle is solve this for A in terms of only known things. Okay, so I substituted F, got rid of F, but I picked up N. So what am I going to get? Where am I going to learn what N is?
Y.
Now I use my Y equation to find out what that normal force is. Again, I know mg and cosine theta, those are all known things, they're all numbers, right? But now I can go ahead and stick that in there, and I'm left with mg sine theta minus mu, and now I substitute in all this stuff, mg cosine theta. All right. Now, can I cancel m out? Sure. And why can I remove m? It is in every term. Right? Mathematically, as long as they're all in every term, I can divide and all of them will go away, which leaves my acceleration being I can write g sine theta minus mu g cosine theta. I could simplify that some more, but I'm not going to. I box it because I think I made it to the answer. And the last step that I need to do is what? I need to check it. I need to plug it into Wiley Plus and hope the green box comes up. No, that's not a check. We should check this for physics. All right. Before, we played around with the angle theta, right? But we've got a new toy. What's the new thing that we could vary in this solution? It's the coefficient of friction. So let's play with that a little bit. We've got a new toy, let's play with it. What happens if we say that mu is, well, pick an easy value for mu. What's an easy value we can think about? 0. The answer whenever any physicist says pick an easy value for something, you say 0 or 1. Do one of those things. Okay? So what happens if we choose 0? Well, this whole term goes away. And what are we left with? Where have we seen g sine theta before? When we did the tauntaun problem last, we got g sine theta. You remember that? If you don't remember that, go back and look at your notes. Not right now. We got g sine theta. By eliminating the friction, that's what mu equals 0 would be, right? By eliminating that, what we got back was the problem we did before where we didn't have friction in it. What does that tell us? We're kind of on the right track, right? It's not a guarantee, but hey, we should get the same answer we got before if the friction were 0. Okay, what happens if it's not 0? Well, the term that involves friction is causing what to happen to the acceleration? It's taking away from it. You see that minus sign on that term? And is that what friction does? Does it change the acceleration? Without friction, tauntaun accelerates however fast it's going to accelerate. But with friction, is the acceleration going to be bigger or smaller? It's going to be smaller. Friction is acting against the motion, therefore against the acceleration. And so that minus sign is making sense to me. I could go play some more with the thetas or whatever, right? But the change here was the friction coefficient, and that seems like that term is capturing the physics of what's supposed to happen. Engineers will get all picky over what the actual numbers are. But I'm pretty satisfied. That's okay. How you doing? Great? How'd chapter 5 homework go? Don't answer that question, I already know. Yeah.
Sorry, I forgot.
It was a little bit short, wasn't it? Am I right?
Yes.
Totally. Why is this not a thing?
Because they're going to fly off.
People would rather make us walk.
There is an obesity epidemic in America. I could see, this is America. I can see the lawsuits. Right? If you ever get a chance to travel to any other country, okay, please do so. But in many other countries, they don't warn you about things. Like, I went to Iceland, and they had signs that said danger, and then that's all the sign said. It didn't say anything else, right? And you know, the implication is if you are stupid enough to go up next to the big cliff with the big waterfall on the bottom, that's your problem.
Yes.
Right? In America, it would be danger. If you go near here, you're going to die. And if you stick your finger through the fan plug, you're going to cut your finger off. Like,
Natural
why do we have
selection.
warning signs on fans?
Happy.
Because somebody somewhere sued the company that made fans and successfully won that lawsuit. It's like reverse Darwinism. Selecting for idiots.
It is.
We need to do this. I talked to the architects about the new science building to do this, and they're like, well, we can't do that.
Build one ourselves.
Slides from the third floor to the bottom.
Isn't like
Ventilator fences.
Google has stuff like that?
What's that?
Google has like.
Does Google Campus have that? Then they must make their employees all sign something that says you can't sue us ever. And I bet you more than anything, it's in the end user license agreement for all Google products. There's somewhere in there that says you cannot sue Google for sliding down our slides. There's a hand over here somewhere. Yeah.
Could you go back to that example? I just had a question on why the mass is canceled out again. Just
Do you want the math answer or do you want the physics answer?
math answer.
The math answer is because the mass is in every term.
Oh, okay.
Physics.
On the right, on the left and right.
Okay. The physics answer.
The physics answer is that gravity is doing the accelerating in this, and gravity doesn't care about mass.
There we go. That's
When I say that, what I mean is the acceleration that the force of gravity imparts to all objects is constant. Here we've got the hill getting in the way and the friction getting in the way, right? Weight does change with mass, but in terms of the acceleration, gravity wants to accelerate everything the same regardless. So it doesn't matter if it's a tauntaun or a beetle or anything else, right? Its mass doesn't matter. Whew. All right. The tauntaun Han Solo situation. Do you like the one with two different angles in it?
Not really.
No? Good. Yeah, be honest. It's great. I didn't quite draw that right, but you get the idea, right? Mass 1, mass 2. Let's do this problem with friction. So again, same problem I did last Wednesday. I'm going to add one force. That's it, just one force. And it's going to go all wrong. It's going to go all wrong. So what did we have last time? We had all those, didn't we? And I believe we made our coordinate system be up because we assumed that Han Solo was winning. And when I went ahead and wrote this out, right, I had mass number 1. This would be slightly different. M1A equals, and then I think I had just a T and a M1G sine theta. Where'd that come from? Well, we had to go find the components, right? Okay, of that thing. M1G. I'm just redoing what we had on Wednesday. That's why I'm going fast, because it should already be there in your notes or off Dropbox or wherever it is you get your stuff. In the y direction, can I go ahead and just write 0 equals? Been writing MA and then canceling it out. But are we far enough along in our expertise level that you're okay with me just writing 0 equals and going for it? Why can I write 0 whenever I see a y acceleration for mass number 1? Because I made sure the acceleration was only in x, right? I'm just going to start writing 0 equals. And then in the y direction, I had n and m1g cosine theta. For mass number 2, in the x direction, didn't have anything. And in the y direction, I had m2a is equal to m2g minus t. Again, our positive y direction was down in order to keep things consistent, right, with the acceleration of the system. So that right there is from Wednesday. We're going to add friction to this. I'm going to tell you that Han Solo is winning. Okay, so we know that the motion of the system is such that mass 1 is sliding up the hill and mass number 2 is falling. With friction, therefore, between the hill and the tauntaun, what direction is it pointing? It's kinetic friction because it's sliding, so it's pointing down the hill. Our force of friction, not because the acceleration's up the hill, but because we know it's sliding up the hill. With friction, you do have to know the direction of motion. It's not enough to know the direction of acceleration. Because you can have something moving and the acceleration can be the opposite of the motion, right? Hope you're over that. That trap where acceleration and motion are the same thing. All right, so with that addition, by putting that frictional force in there, what changes? Does anything with mass 2 change? No. So mass 1, it's the x equation, isn't it? We have t, we have m1g sine theta, and now we have f, and there's going to be a minus sign on it. Why? Because it points down the slope. Friction points down the slope. Good. What I was listening for and what I was glad I didn't hear, and I saw it in some of your brains just now, because it's friction. Because it's kinetic friction. There you go. So that's it. Just added the little f. Just a minus f on the end. How many unknowns are there?
3.
We don't know A. We're looking for it. We don't know T. We don't know F. We don't know N. And A's and T's are repeated in mass 2, so they're all the same thing, right? Okay? So everything with a blue check mark is unknown. So how many total unknowns are there? 4. How many equations do I have to work with? 3. 0 equals 0, though a valid and beautiful equation. Doesn't help here. 4 unknowns, 3 equations. Can you do it? No, it's impossible. I don't care how good you are. Because what else do you need? A 4th independent equation? And where are we going to get it from? Fun! You keep saying it enough, you might believe it. All right. Is this looking familiar?
Yes.
4 unknowns, T, A, N, and F. Solve so that only A remains. Where have you seen this before? Lab 1. Problem number 4. I just saved 10 minutes of lecture. You've already done the math, right? So go back to that, and you'll get the answer. One form of the answer. There, depending on how you went through the algebra, you could get all kinds of stuff. Okay? One way to write it down would be like that. Once I know what that A is, I can go ahead and chuck it back into an equation for T and find it for T. But see lab 1, right? For that part right there. So when friction gets added to the mix, your bread and butter becomes 4 equations with 4 unknowns. Went from 2 equations with 2 unknowns to 4 equations with 4 unknowns by adding 1 force. be careful what you wish for, I guess is the moral of today. There's something nice about the innocence of ignoring friction. Carlo?
What was it, when you make the coordinate system for the first mass, and you go up is x, did you say that positive x is also downward for the second
Yeah,
mass?
you don't have to call it y, you can call it x.
Okay,
As long as you make a positive direction that way and stay consistent.
okay.
Yeah. I had a physics class in I want to say it was like my third year of teaching. It's earlier on in my career. And they were getting upset at me. I'm used to it. And they kept complaining that I was ignoring real things. Mr. Bailey, you're ignoring really, never putting friction. So one day I kind of had enough of it, and I was like, okay, do you really want to see what happens when I don't ignore stuff? Like, yeah, let's see what happens.
You made them regret it.
Oh, yeah. Used to be chalkboards, didn't used to be whiteboards. I started over there, and I just started going. Right? And right about here is where the differential equations appeared. Okay? And after that, they were just like, stop! I was like, you asked for this. Right? And I just kept going. And they never asked again. They were just like, oh, that's okay. Yeah, we're good with no friction. Yeah, no friction. Right? Okay? Yeah, it gets really bad really fast. And the gains that you make, again, it kind of depends. Does it really matter that the coefficient of, or that the force of friction is changing when you're stopping a car? Well, the answer is not really until the car is going slow enough. Right? In that first initial part of braking, like the first 80%, it's really safe to assume that the force of friction is the same throughout the braking. Like it doesn't vary by hardly, like less than 1/10 of 1% variation over that. It changes a lot as the car gets really slow and comes to a stop. And so if you can save time on places where it's not changing a lot, you're comfortable with just a little bit of deviation from what's real, and then you can focus all of your effort in the part where there is significant change, now it's worth it to go into those deeper concepts and different ideas. You'll find this as you go through your scientific and engineering careers, okay? Scientists will be like, we can ignore that part. And you're like, well, you just ignored everything. Yes, but ignoring it doesn't change its significance. We've got to focus on the parts that are significant. All right. I'm almost done with chapter 6. Great. What we need to do is we need to take what we've learned into the realm of circles. Again, sort of this theme of introducing circular motion to you in small bits before we dump it all on you later. So, kind of the best example of this, I think, okay, 2 examples I want to do, and I may or may not get through the second example this time. Well, we might spill over a little bit chapter 6 into Wednesday, but then I'll get into chapter 7. Is a roller coaster. This is a great example of a vertical circle, in the sense where the circular motion is in the vertical plane. Okay? So whether this is a roller coaster going around its track, or an airplane doing a loop-de-loop, or even a car going over a circular hill, you'll see those. Okay? All of those things are examples of circular motion in a vertical orientation. So Ferris wheels, all kinds of stuff. So what's going on here? Well, circles and circular paths, to be fair, we should probably consider points everywhere on the circle, but we're going to laser focus in on the 2 easier spots. We're going to look at the roller coaster car at the bottom of the loop and the roller coaster car at the top of the loop. And in this example, you've noticed I haven't given you any numbers hardly at all in these chapters. You can put the numbers in later. In this example in particular, I don't even care what the numbers are, because what I'm after is what's going on at these two situations? What are the passengers experiencing? And how do I know that what they are experiencing is correct? I want to use physics and mathematical methods to bring out a big conceptual connection, which is, again, kind of the artistry of physics. Is we don't really care about numbers. What we want to know is what's going on at a fundamental level. So we're going to do this at the top, and then we're going to do it at the bottom. Now, in order for something to travel in a circle, what direction is the acceleration of the object? It's towards the center. For now, constant speed. As soon as we start changing the speed, it's going in a circle. We've got to do other stuff. But for now, the acceleration point towards the center. What does that mean, therefore, that the direction of the force has to be? What force, Mr. Baylor? There's a force. How do I know there's a force? Because there's an acceleration. If there's an acceleration that points towards the center, then what must I have? A non-zero, unbalanced force that points in the same direction. What are we going to call that force? Centripetal force. But I want you to know right now, it is not a new force. It's a different name for a force that already exists. This is where it's critical that we come back to objects. Let's do the roller coaster at the bottom first. Okay? So at the bottom, we draw a free body diagram. Okay? We ask ourselves, what objects are pushing or pulling on the roller coaster car? Well, name an object that's pushing or pulling on the roller coaster car at the bottom. Okay, so the Earth. And the Earth causes weight, which is mg. Okay? That one did not point towards the center. The track. The car is in contact with the track. So, there's got to be a normal force. All right. Name another object that is pushing or pulling on the car. Okay, well, the people are in the car. Friction, people are saying friction. What direction would friction point if this thing were sliding? Opposite the direction of motion. We're not going to worry about that. You can either say it's frictionless or friction would be in a horizontal plane. And I just want to do the vertical stuff right now. I just finished telling you that there has to be a force that points towards the center. What do we call it? Centripetal force. So which force is the centripetal force?
The normal.
It's the normal force. Don't go and invent a new force. This is wrong. Don't do this. Do not write this down. You're not going to come in here and go, well, there's got to be an F sub c. If you write that force down, what do you have to check?
What object?
What object caused it? The centripetal object. No, it's not there. Okay? The normal force, a force that already exists because there's an interaction between two physical objects, is the thing that points towards the center. It's the centripetal force. If I have a rock tied to the end of a string and I'm whirling it around on the end of the string, name the force that points towards the center. Tension. Tension is the force that points towards the center. It pulls the rock inward, right? No matter where it is in its circular path. Don't go inventing forces that aren't there. The centripetal force is a label change. It's simply a shorthand way of saying any force that points towards the center of the motion. Those forces, by Newton's third law, still have to be caused by other objects. All right. What direction is the acceleration? Towards the center. So which way are we going to make positive? Up. So when I write down here at the bottom, I'm going to do M, A, and I'm going to say A sub C as a reminder that I'm doing a circle and that the acceleration is pointed towards the center, the centripetal direction. And then what forces do I have? How many? 2. I've got normal and I've got mg. Normal, positive or negative? Positive. Mg? Negative. All right, let's do it at the top. What's different at the top? First of all, which way does mg point? Down. And is mg still there? Is the Earth still pulling on the roller coaster? Oh yeah. Yeah, no, it doesn't just turn off at the top. But it feels like we're falling. We're getting there. Don't worry. What else exists at the top? Did I hear it out there? The normal force. Does normal force go away? They're in contact with each other, right? So, what direction does the normal force point? The roller coaster car is now upside down. The surfaces are coming into contact upside down. What direction is the track pushing on the roller coaster car? Down. Perpendicular to the surface of contact. So the normal force points down. What's the centripetal force? Both of them. What direction is the centripetal acceleration? Down. What direction are we going to call positive? Down. So now I write M, A, and what do I write?
Plus mg.
Supposed to be a G. There we go. Oh, that's a tricksy little hobbitses. Question. So, are those two equations identical? What are they saying? Let's take a look at the bottom one here. If I solve this for the normal force, I'm just going to play around here, then what I'm going to get is MA plus mg. And if I did the same thing at the top, I solve for the normal force up there, I'm going to get MA minus mg. What is the bottom one saying? And what is the top one saying? Bottom one says the amount of force that the track applies on the roller coaster car is going to be the sum, the addition of the object's weight and this term that I don't really understand, Mr. Baylor. What is that? It's an inertia term, right? MA together is the inertia of the object. Sort of. It's a lie. It's a good one. In other words, at the bottom, what?
Could you spell inertia for me real quick?
I-N-E-R-T-I-A.
Okay.
English. So, the normal force at the bottom of the loop is bigger than it would be at the top. For a rider in the roller coaster, what does that mean? Feels like at the bottom of the loop-de-loop, you get pinned into your seat, right? But as the loop-de-loop goes around, what happens as you go to top? Whee! Why is everybody shouting, whee? Because the feeling of weightlessness is starting to occur. You go from being pushed into your seat to not being pushed into your seat as much. The normal force is big, and then it's smaller, and then it gets bigger, and we go, whee, and then we throw up. That's what that's saying right there. It says that the normal force is different at the top and the bottom. What human beings tend to think of as their weight really isn't their weight at all. And I'm not making any judgment calls about America and our obsession with calories or any of that kind of stuff, right? What I'm talking about literally is what we think of as our weight. We don't ever think of our weight as the force of gravity acting on us. We think our weight is what the floor is pushing back on us. Again, we're back to the elevator situation. When you get in the elevator, you push the button, and the elevator floor begins to move up. Do you feel heavier? Yes. Did you gain mass? No. Did the earth gain mass? No. Did the force of gravity between you and the earth change? No. So why did you say you feel heavier? Because the normal force on you increased. This is called apparent weight. What people will often tell you about what's happening to their weight isn't what their weight at all. It's the contact force between them and their environment. So when people get on roller coasters, they go, oh, I got weightless at the top. What happened is the normal force got less. In fact, we can find out exactly how fast the roller coaster needs to be going in order for true, well, I don't want to say true weightlessness because that's not a thing. In order for someone to feel like they are completely weightless. What must be true at the top in order for someone to not experience any normal force? If the normal force goes to 0, then what does this statement tell us? That MA is equal to mg. Whoops. That the mass of the rider makes absolutely no difference. So effectively, the rider at the very top is in what? Free fall. People who are in free fall often say, I'm weightless. Well, okay, no, you're in free fall and you're going to hit the ground. Okay? Force of gravity very much is acting on you. Okay? But what they mean is nothing has to hold them up. That's apparent weight. How do we find out exactly what the speed needs to be? Well, remember that this is a centripetal acceleration. That means that that acceleration has to be related to the object's tangential speed. Which means that the speed required in order to achieve that instant of 0 normal force is the square root of the radius of the circle divided times gravitational constant of whatever planet you're on. Which means if you're going to put a roller coaster on the moon, you have to do what to the radius of your circle? Little g is smaller, which means you can have slower roller coasters, but that's no fun, right? And if you want your roller coaster to go fast on the moon, you better have a big R to compensate that little g. So there you go. I have given you a business idea.
Huge.
Roller coasters on the moon. Okay? It's also the speed that will guarantee that the roller coaster car doesn't fall off the track.
Sling it into orbit.
If the roller coaster car was just riding on the top of the track and had nothing in the mechanism to keep it attached to the track, then the roller coaster must have a speed faster than that. Because that's the speed it needs to just have 0 at the top, right? Any faster than that, and there's going to be some normal force. Any slower than that, what's going to happen? It's going to fall off the track. Because the normal force has disappeared. Right? Now, for those of you that are worried, roller coasters have mechanisms that keep them on the track regardless of whether they're upside down. They've got 2 sets of wheels, one on the top, one on the bottom, so when it inverts, right, there's always something that's attaching it to the track. and they have that thing that goes over you that holds you in, right? That they always make sure that there's space in that harness, right? They don't strap you into the chair because that wouldn't be any fun, okay? What they do is they put that thing over there so that when you fall, you kind of just fall into the harness. You still get that feeling of, ooh. You notice that this loop-de-loop is not exactly circular. See how it's teardrop shaped? Anybody know why they do that?
Make you exit faster.
It actually does two things. It reduces the crush at the bottom of the loop. Okay? You can see there how the normal forces are pointing not directly up and down and pointing off the side, which again makes it a little bit more comfortable as you're entering and exiting the loop. You don't feel as pushed down into your seat. Because people complain that that doesn't feel good, right? And then the radius of that loop is constantly changing. Okay? And what that does, that teardrop shape, what it does is it kind of widens out the zone at the top where the person experiences that no normal force situation or very small normal force situation. Whereas in a circular loop, there's really only at the top that occurs. In this teardrop shape, you get a little wider zone of weightlessness. Yeah, you feel it for longer, right, as opposed to just in an instant. Where else does this rear its ugly head? Banked turns. Anybody here live on the East Coast or born and raised on the East Coast? Okay, good. I can make fun of people from the East Coast. On the East Coast, if you ever get to go a chance to get there, you will notice two things about their roads. Number one, they're way too small. Don't drive in Boston. That's my advice. The second thing is, all the roads, besides being narrow, are like perfectly flat. And then they put two big ditches on the edge. Okay, so you got this big elevated road with big ditches. I'm convinced that's where you can catch the cars. In the West, we have roads that are more like this. They're wider, and you go up into the mountains, and the roads are not perfectly flat and level. They're banked. Okay? Why do we bank the turns in the West, and why are roads so flat in the East? Because we're better. Because in the East, they built their roads back in the day when horses were a thing. We didn't really get roads in the West until the 1980s. 40s, but still. Okay? Paved roads. And it turns out banking the turn makes the turn safer. Now, I'll show you why on Wednesday, but I want to show you this next picture because I go off to the internet to look for things about examples of what's going to happen to. Hello? Everybody calls here once in a while. So, I got this picture.
Oh, no. Dang. Whoa.
Now, if buses did that, I would take mass transit.
Yes.
Right? How is that bus not falling over?
Physics.
And we'll leave it there. I'll see you on Wednesday. I'll answer that question and then we'll start chapter 7.